Standing along the eastern bank of the Moselle River near Pont-à-Moussin, France, Colonel Friedrich von Mellenthin found himself confronting something that defied every calculation his staff had made. The date was September 8, 1944, and what he observed that day would compel him to document in his evening diary entry as Chief of Staff to General Hermann Balck's Army Group G, a reality that was rapidly dismantling German defensive doctrine. American engineers were assembling a bridge across the water with such extraordinary velocity that Mellenthin struggled to comprehend the implications. His diary notation captured the Wehrmacht's mounting apprehension in stark terms, noting how the enemy's capacity for bridge construction had surpassed every projection they had formulated. The Americans were establishing multiple river crossings at the same time, bringing each structure to completion before German artillery could mount any meaningful interference. This observation represented far more than a tactical inconvenience. What Mellenthin was witnessing constituted nothing less than a fundamental transformation in how modern wars would be fought. From one end of an 800-mile battlefront to the other, American engineer battalions were systematically proving that rivers, those ancient barriers that had shaped military campaigns since the dawn of organized warfare, no longer possessed the power to dictate where armies could and could not advance. The Wehrmacht's defensive philosophy, built upon centuries of experience utilizing natural water barriers, was being rendered irrelevant while German officers watched in dismay. The scale of this engineering revolution would become evident in the statistics compiled between August 1944 and May 1945, a period during which American engineers would throw more than 300 major crossings over rivers throughout the European theatre, each one supporting the relentless Allied push deeper into German territory. German intelligence services initially documented 119 separate bridges constructed during just Patton's autumn offensive, a figure that seemed so implausible that analysts questioned whether their information could possibly be accurate. Yet week after week, that number was not only confirmed, but exceeded as more bridges materialized across waterways the Germans had expected to defend for weeks. General Hermann Balck himself embodied the finest traditions of German military excellence. One of the Wehrmacht's most decorated panzer commanders, he had earned the Knight's Cross adorned with oak leaves, swords and diamonds through his exploits on the Eastern Front. His tactical brilliance had been demonstrated conclusively at the Chir River, where he had orchestrated the destruction of entire Soviet tank armies. Yet even this experienced warrior found himself facing circumstances that lay entirely outside his considerable experience. In interviews conducted after the war ended, Balck made a remarkable admission that spoke volumes about what American engineering had accomplished. His forces had spent weeks preparing defensive positions along the Moselle River, and traditional military science, refined over generations of European warfare, insisted that such a river obstacle would delay the American advance for a minimum of 2 weeks. Instead, the Americans crossed it in 2 days. The revolution that Mellenthin observed at the Moselle had actually commenced months earlier in Normandy, where American commanders had absorbed critical lessons about mechanized warfare's true requirements. General George F. Patton, who had recently taken command of the newly activated Third Army, understood better than most that maintaining operational momentum represented the paramount concern in mobile warfare. However, Patton's comprehension extended to a deeper truth that many commanders overlooked. Momentum divorced from logistics was essentially meaningless, and in the river-crossed terrain of Europe, logistics invariably meant bridges. Patton gathered his engineer commanders near Avranches on July 31, 1944, the day preceding Third Army's official operational status. Among those present were Colonel Garrison Davidson, serving as Third Army engineer, and Lieutenant Colonel George Walker of the 1139th Engineer Combat Group. Patton's instructions to these men carried his characteristic directness and clarity. The Germans would destroy every bridge between the Allied positions and Berlin. That much was certain. The engineer's task, Patton explained, was straightforward in concept if demanding in execution. They needed to replace those destroyed bridges with such rapidity that the enemy would be uncertain where to direct their counterfire. Patton wanted his engineers to make geography itself irrelevant to Third Army's operations. The American engineering advantage that would prove so decisive had roots reaching back several years. Since 1942, the U.S. Army had undertaken a comprehensive revolution in how combat engineers were trained and prepared for their mission. At Fort Belvoir's Engineer School, entire battalions underwent intensive practice in rapid bridge construction, working under every conceivable environmental condition and tactical scenario. The material superiority Americans enjoyed proved equally decisive in determining operational outcomes. American industry had engaged in bridge equipment mass production on a scale without historical precedent. The Bailey Bridge, originally a British innovation that American factories had manufactured under licensing agreements, revolutionized what was possible in military bridging operations. Constructed from 10-foot steel panels, each weighing 600 pounds, the Bailey Bridge could be assembled entirely by hand without requiring any crane equipment. By the time the war reached its conclusion, American manufacturing facilities had produced sufficient Bailey Bridge components to span the English Channel 50 times over if laid end to end. American innovation produced the M2 Treadway Bridge, which represented another leap forward in bridging technology. This system consisted of pneumatic floats supporting steel decking and, remarkably, could be assembled directly from trucks without extensive preparation. The 991st Engineer Treadway Bridge Company had refined their procedures to the point where they could construct a 540-foot bridge capable of supporting 40-ton Sherman tanks in under 4 hours from start to finish. Captain Hans Müller, a Wehrmacht pioneer officer who fell into American captivity during December 1944, provided intelligence that illuminated the gulf between German and American engineering capabilities. He explained that their best German engineer battalion, provided with all necessary equipment and working without any enemy interference, required somewhere between 48 and 72 hours to construct a heavy bridge. The Americans accomplished the same task in 4 hours while German artillery was actively firing on them. Müller's assessment was blunt in its implications. The two armies were not fighting the same war when it came to engineering capabilities. The Seine crossing, executed in late August 1944, furnished the first major demonstration of what American engineers could accomplish. The German Seventh Army had systematically destroyed every bridge along a 60-mile stretch of the river. General der Waffen SS Paul Hauser had calculated, based on sound military reasoning, that the Americans would require at least 10 days to force a crossing under these conditions. His calculations proved wildly optimistic from the German perspective. The 1,139th Engineer Combat Group threw 5 separate bridges across the Seine River in just 72 hours. At Malone, engineers belonging to the 537th Light Ponton Company constructed a footbridge while under direct German machine gun fire, and they completed the structure even after an 88mm shell destroyed a 50-foot section while construction was still underway. Private Lawrence Jefferson earned a Bronze Star for his actions during this operation, and his description of the experience conveyed the intensity of what these engineers endured. German shells were landing in the water all around them as they worked. When explosions blew out a section of bridge, the engineers simply rebuilt it and continued. They had to keep working, Jefferson explained, because otherwise infantry would die attempting to cross by boat. The sophistication of American engineering operations extended far beyond simple construction speed. The 161st Chemical Smoke Generating Company possessed the capability to blanket an entire river valley in dense smoke within minutes of being called upon. Counter-battery radar units immediately pinpointed the location of German guns the moment they fired, directing devastating artillery responses that made German gunners' lives extremely hazardous. Lieutenant Wilhelm Hoffmann of Artillery Regiment 17 explained the frustration German artillerymen experienced in attempting to disrupt American bridge construction. They would carefully calculate firing solutions for their guns. Then suddenly, thick smoke would cover everything, rendering their calculations useless. When they fired, they were shooting blind. Hours later, when the smoke finally cleared, they would discover completed bridges with American tanks already crossing to the eastern bank. The Moselle River operations conducted throughout September 1944 demonstrated American engineering capabilities in their full maturity. The river itself presented formidable natural obstacles to any crossing attempt. It measured 200 feet wide with steep banks on both sides, possessed a swift current, and the Germans had established extensive fortifications along its length. General Balck had positioned the 47th Panzer Corps along the Moselle, feeling confident that the river barrier would bring Patton's advance to a halt. During a staff conference held on September 5th, he declared his conviction that while the Americans were excellent soldiers, they were not superhuman. The Moselle would stop them just as rivers had stopped armies throughout military history. What followed in the days ahead shattered every assumption German commanders held. On September 7th, advance elements of the 81st Infantry Division reached Pont-à-Moussin on the Moselle's western bank. Within mere hours of their arrival, the 135th Engineer Combat Battalion had assault boats ferrying troops across the water. By midnight, footbridges spanned the river, allowing continuous infantry movement. By dawn on September 8th, heavy pontoon bridges were carrying tanks to the eastern bank. This was the scene that so disturbed Colonel von Mellenthin. The American engineering system functioned with industrial efficiency that German observers found almost incomprehensible. The 1,303rd Engineer General Service Regiment operated mobile bridge repair teams that could replace damaged bridge components in 2 hours. Truck-mounted air compressors inflated bridge floats in minutes rather than hours. Every single piece of equipment was standardized and interchangeable, designed from the ground up for maximum assembly speed. Master Sergeant Earl Hall of Company B, 1303 Engineer General Service Regiment, explained the philosophy that guided their work. Everything centered on time, because time translated directly into lives. They had developed systematic procedures for absolutely everything involved in bridge construction. Parts were numbered, tools were color-coded, and laminated instruction cards meant that even a replacement soldier fresh from the rear could contribute effectively within hours of joining a unit. The human cost of maintaining this pace was severe and should not be forgotten. Engineers worked in completely exposed positions. During just the Moselle crossing operations, engineer units absorbed 15% casualties. At the Saar River in December, the 994th Engineer Treadway Company lost 18 men in a single hour, yet continued bridge construction without any pause in their work. Lieutenant Colonel Kenneth Fields, commanding the 135th Engineer Combat Battalion, suffered shrapnel wounds during bridge construction near Metz, but refused evacuation for 6 hours until the bridge was complete. His words became legendary among engineer units. The infantry needed this bridge that night, not the following day. Engineers finished what they started, period. German combat engineers, watching their American counterparts in action, developed profound respect for what they witnessed. Major Friedrich Schulze of Pioneer Battalion 305 told his interrogators after capture that Germans had thought Americans were soft soldiers who relied excessively on material advantages. But American engineers stood in freezing water for hours at a stretch, working through artillery barrages that would send infantry running for cover. They had unlimited equipment, certainly, but Schulze observed they also possessed unlimited determination to complete their missions regardless of cost. The Rhine crossing operations conducted in March 1945 represented the culmination of everything American engineers had learned and perfected over the preceding months. The fortuitous capture of the Ludendorff Bridge at Remagen on March 7th was certainly fortunate, but what happened next revealed American adaptability and systematic thinking. Despite German artillery fire, air attacks, and even V-2 rockets directed at the bridge, American engineers immediately began constructing supplementary bridges in the vicinity. When the Ludendorff Bridge finally collapsed on March 17th, 8 additional bridges already spanned the Rhine at Remagen, ensuring uninterrupted traffic flow. Patton's crossing at Oppenheim demonstrated deliberate American engineering might applied with characteristic audacity. On the night of March 22nd, without any preliminary bombardment that might alert German defenders, the 5th Infantry Division crossed the Rhine. By dawn on March 23rd, engineers had completed a 1,000-foot heavy pontoon bridge. Within 48 hours of the initial crossing, 3 major bridges were carrying Third Army across the Rhine. Colonel Hans Felber, who served as chief engineer of Army Group B before his capture in April, testified to something that German officers found difficult to accept. Germans were excellent engineers in their own right, Felber insisted, but American engineers operated according to a completely different philosophy. The Americans had brought industrial production methods directly onto the battlefield. While German engineers were still calculating loads and stress points, American tanks were already driving across completed bridges. The statistics compiled for March 1945 alone told an extraordinary story. American engineers constructed 62 bridges across the Rhine and its tributaries during this single month. The longest, a 1,900-foot Bailey Bridge at Wesel, was completed in 9 hours and 30 minutes despite continuous German fire throughout the construction period. These bridges carried over 1 million men and 300,000 vehicles into the heart of Germany, enabling the final campaigns that would end the European War. Beyond bridge construction, American engineers transformed the battlefield in countless other ways. They built 17,000 miles of roads where none existed or where existing roads had been destroyed. They cleared millions of mines from fields, roads, and urban areas. They constructed 121 airfields to support tactical aviation. They repaired 8,000 miles of railroad track to ensure supply lines could function. The organizational philosophy undergirding all this work proved absolutely crucial to its success. American engineers operated with a degree of autonomy that German officers found shocking. A sergeant in an American engineer unit could make decisions that would require a captain's approval in the Wehrmacht. This decentralized decision-making capability, combined with standardized equipment that any unit could employ, created unprecedented flexibility in responding to tactical situations. Colonel Wilhelm Wegener, former Chief of Staff of the German 5th Panzer Army, made an observation that captured something essential about the American military system. The American Army functioned as an industrial democracy in uniform. Every soldier understood the overall mission and could act independently to accomplish it. The German Army, by contrast, remained aristocratic in its structure and thinking. Orders flowed downward through rigid hierarchies. Initiative among junior officers and enlisted men was actively discouraged rather than cultivated. Traditional German defensive doctrine had always assumed that rivers would provide time for forces to reorganize and establish new defensive positions. American engineering capabilities eliminated that assumption entirely. General Hasso von Manteuffel explained the strategic implications with remarkable clarity. In all previous wars, reaching a major river meant an operational pause while forces prepared for the crossing. Against the Americans, no such pause existed. They pursued across rivers as though rivers were merely lines drawn on maps with no physical reality. The impact on German morale extended far beyond tactical concerns. Young Wehrmacht soldiers watched American engineers construct bridges under fire that German engineers couldn't build even in peacetime conditions with unlimited time. Lieutenant Martin Jennings wrote from captivity about how German soldiers had been told that Americans were cowards who relied purely on material superiority rather than courage. But Jennings had personally watched American engineers continue building while shells fell among them. When one man fell wounded or dead, another immediately took his place without any hesitation. This was not the behavior of cowards. German civilians witnessed bridges appearing overnight where no bridges had existed the previous day. Anna Richter, a schoolteacher in the town of Worms, recorded her observations in a diary that survived the war. On March 25th, she noted American vehicles crossing a bridge that definitely had not been there the day before. All day long, vehicles crossed in an endless stream. Her father, who had fought in the Great War, watched silently for a long time before finally saying that Germany had challenged a giant and was now paying the price for that challenge. The initial 119 bridges that German intelligence had tracked during autumn 1944 represented merely the beginning of what would become an engineering achievement of staggering proportions. By the time the war in Europe concluded, over 300 major bridges had been constructed by American engineer units. These engineers had fundamentally altered the nature of warfare itself. In his final report, written before taking his own life, Wilhelm Keitel acknowledged that the enemy's technical superiority, particularly in engineering capabilities, had rendered traditional defensive warfare impossible. German defeat, Keitel concluded, had been inevitable from the moment this reality became apparent to anyone willing to see it clearly. Post-war analysis conducted by various agencies confirmed what German commanders had experienced firsthand. The U.S. Strategic Bombing Survey, tasked with assessing the effectiveness of different elements of the Allied war effort, reached a striking conclusion. While air power and armoured forces received most of the public attention and historical focus, combat engineers were quite possibly the most decisive arm in achieving Germany's defeat. General Franz Halder, reflecting on what he had witnessed, wrote that the American engineer represented something genuinely new in military history: the successful marriage of industrial production capacity and combat capability. Every bridge those engineers built brought Detroit and Pittsburgh one river closer to Berlin. For the American engineers who had accomplished all this, their achievement remained a source of lifelong pride tempered by modesty about their role. Staff Sergeant James Patterson of the 249th Engineer Battalion, speaking at a unit reunion held in 1995, expressed what many of his comrades felt. They weren't heroes in the traditional sense, Patterson insisted. Heroes charged machine gun positions. Engineers just built bridges. But every bridge they constructed meant American soldiers got home to their families sooner, and that made the work worthwhile regardless of the cost. The legacy of American engineering operations in Europe transcended individual memories and unit histories. NATO military doctrine incorporated the lessons learned from these operations into its core planning. The Bundeswehr, when it was eventually formed, emphasized combat engineering to a degree that would have been unimaginable in the old Wehrmacht. Colonel Hans Spädel, who had served in the Wehrmacht and later became a NATO commander, wrote about what the Americans had taught the German military. In modern warfare, the side that maintains momentum wins the battle. Momentum requires mobility across all terrain. Mobility requires engineers who can overcome natural and man-made obstacles. This was the fundamental lesson of 1944 and 1945. The story of those bridges, those engineers, and that campaign reverberates through history as a testament to what American industrial democracy could accomplish when fully mobilized for war. Those 119 bridges that German generals never expected to materialize became powerful symbols of a fundamental truth about warfare in the industrial age. Production capacity and organizational flexibility trump traditional military virtues when applied systematically and relentlessly. Young Americans, many of them farm boys from Iowa, factory workers from Detroit, and college students from California, had taken American industrial might and applied it directly to the sharp end of warfare where battles are actually won and lost. These men didn't merely win a war through their efforts, they revolutionized how wars would be fought for generations to come. German generals who had initially dismissed American engineers as nothing more than construction workers in uniform witnessed those same engineers systematically reshape Europe's physical terrain to suit American operational needs. Rivers that had stopped armies since Roman legions marched across Europe became brief delays measured in hours rather than weeks. This was warfare transformed by industrial power applied with intelligence and determination. The deeper story here concerns American democracy itself at war. The American system proved decentralized by nature, flexible in application, innovative in problem-solving, and backed by seemingly unlimited industrial power. German generals found themselves unable to conceive of how such a system could function effectively because their hierarchical military tradition provided no framework for understanding an army where a sergeant equipped with a bulldozer and bridge panels could reshape the battlefield according to tactical necessity. Each bridge these engineers constructed carried a message that German commanders eventually understood, even if they never accepted it. American productive capacity was essentially limitless, and American determination was unbreakable once fully engaged. The engineers built far more than bridges spanning rivers. They built the physical pathway to a new era in warfare where industrial might and human ingenuity would trump terrain and tradition. The German generals, who never expected American engineers to throw up bridges almost instantaneously while Patton's tanks thundered forward across them, learned warfare's new arithmetic, but they learned it far too late to alter the war's outcome. The combat engineer had become as essential to achieving victory as any warrior who ever took the field throughout history. German forces found themselves facing not just an army, but an entire system of warfare that literally built its way to victory, one bridge at a time, and no amount of courage or tactical skill could overcome that systematic application of American industrial power to military problems. The transformation that occurred between 1944 and 1945 permanently altered how military planners would think about rivers and obstacles. Where previous generations of commanders had viewed rivers as natural stopping points requiring extensive preparation for crossing operations, American engineers proved that with proper equipment, training, and determination, rivers could become mere inconveniences rather than serious obstacles. This shift in thinking influenced not only American military doctrine, but the military thinking of every nation that studied the European campaign. The systematic nature of American engineering operations deserves particular emphasis. This was not a matter of individual brilliance or fortunate circumstances. The success of American engineers resulted from conscious planning that began years before the first bridge was built in combat. The training programs at Fort Belvoir and other installations created a core of engineers who understood both the technical requirements of bridge construction and the tactical necessities of combat operations. These men learned to work under fire, to maintain focus when comrades fell beside them, and to keep building regardless of obstacles. The standardization of equipment represented another crucial factor that German forces never matched. When every Bailey Bridge panel was identical, when every float in a treadway bridge was interchangeable, when every tool and every procedure was standardized across all engineer units, the result was an organization that could function with remarkable efficiency under the worst possible conditions. A damaged bridge section could be replaced quickly because the replacement parts were identical to the originals. A unit suffering casualties could be reinforced by men from another unit who already knew the equipment and procedures. This standardization, so typical of American industrial thinking, proved invaluable on the battlefield. German engineers, by contrast, often worked with equipment that varied from unit to unit, with procedures that reflected local preferences and traditions, with training that emphasized individual expertise rather than systematic approaches. The results spoke for themselves. German engineers were skilled and brave, but the system they worked within could not compete with the systematic American approach backed by overwhelming industrial production. The speed of American bridge construction affected German defensive planning in ways that extended far beyond the immediate tactical situation. When German commanders knew that a river would only delay the American advance for hours rather than days or weeks, they had to rethink their entire defensive strategy. Positions that would have been tenable with adequate time to prepare became untenable when that time was stripped away. Counterattacks that might have succeeded if launched while Americans were still attempting to cross rivers became impossible when Americans had already established firm bridgeheads and were pushing inland before German reserves could arrive. The psychological impact on German soldiers watching these operations cannot be overstated. Soldiers fight with greater determination when they believe their sacrifices serve a purpose, when they believe their defensive positions can hold. Watching American engineers build bridges faster than seemed physically possible, watching those bridges survive German artillery fire through sheer redundancy and rapid repair, watching American forces pour across those bridges in seemingly endless columns, all of this contributed to a growing sense among German soldiers that resistance was futile. This erosion of morale, difficult to quantify but clearly evident in prisoner interrogations and captured documents, represented another way in which American engineering contributed to victory. The coordination between American engineers and other branches of the army demonstrated sophisticated combined arms operations at their finest. When engineers needed smoke to conceal their work, chemical units provided it immediately. When German artillery threatened bridge construction, American counter-battery fire suppressed those guns within minutes. When bridges needed defending against German counterattacks, infantry and armor units moved to provide that defense without being asked. This level of coordination resulted from extensive training, clear communication, and mutual respect among different branches of the service. The casualties suffered by American engineer units must be remembered and honored. These men were not rear-echelon troops safely distant from combat. They worked at the most dangerous points on the battlefield, exposed to enemy fire while performing tasks that required concentration and precision. A man carrying a 600-pound bridge panel cannot take cover quickly when artillery shells begin falling. A man standing waist-deep in freezing water while assembling bridge floats cannot run when machine gun fire erupts. The engineers accepted these risks because they understood that infantry depended on them, that tanks depended on them, that the entire operational plan depended on their completing their work regardless of danger. The recognition these engineers received, both during and after the war, never quite matched their contribution to victory. Tank commanders and infantry leaders earned medals and fame. Engineers, for the most part, simply did their jobs and moved on to the next river, the next bridge, the next obstacle. Yet their contribution was fundamental to everything else the army accomplished. Without bridges, Patton's tanks went nowhere. Without bridges, infantry could not maintain pressure on retreating German forces. Without bridges, supplies could not reach forward units. The engineers made everything else possible. The technical innovation displayed by American engineers extended beyond bridge construction itself. They developed new techniques for rapid soil analysis to determine whether riverbanks could support bridge approaches. They invented new methods for anchoring bridges in swift currents. They created improved procedures for working at night, allowing bridge construction to continue around the clock. They adapted equipment designed for one purpose to serve other needs when circumstances demanded. This innovative spirit, this willingness to experiment and improvise, characterized American forces throughout the war, but found particular expression in engineer units. The relationship between General Patton and his engineers deserves special mention. Patton understood, perhaps better than any other American commander, that engineers were essential to his aggressive operational style. He demanded the impossible from his engineers, and they delivered it consistently. He protected engineer units from being diverted to other tasks. He ensured they received the equipment and replacements they needed. He personally visited engineer units working under fire to express his appreciation for their efforts. This mutual respect between Patton and his engineers created a partnership that proved devastating to German defences. The comparison between American and German engineering capabilities illuminates broader differences between the two military systems. German military tradition emphasized individual excellence, technical perfection, and traditional military virtues of courage and endurance. The American system emphasized standardization, systematic procedures, industrial efficiency, and practical results. Both approaches had merit in different contexts, but in the circumstances of 1944 and 1945, the American approach proved decisively superior. German prisoners questioned about American engineering capabilities often expressed bewilderment mixed with admiration. They understood the technical accomplishments they had witnessed, but struggled to comprehend the organizational system that made those accomplishments possible. How could an army function effectively when junior officers and even enlisted men made significant decisions without consulting higher authority? How could standardized procedures produce results when every tactical situation was unique? These questions reflected a genuine cultural gap between German hierarchical thinking and American organizational flexibility. The long-term influence of American engineering operations in Europe extended into post-war military development worldwide. Nations that had observed American bridge-building capabilities sought to develop similar capabilities for their own forces. The Bailey Bridge became standard equipment in armies around the world. Training programs modeled on American approaches were established in numerous countries. The basic insight that rivers need not be decisive obstacles if engineering capabilities were sufficient became conventional wisdom among military planners globally. The story of American engineers in Europe also illustrated how technological superiority alone was insufficient for success. German forces possessed excellent equipment and highly trained personnel. What they lacked was the systematic organization, the industrial production capacity, and the organizational flexibility that American forces brought to every operation. Technology mattered, but the system employing that technology mattered even more. Looking at specific examples of American engineering achievements provides concrete illustrations of what these statistics and generalizations represent. Consider the bridge at Wesel, that 1,900-foot structure completed in 9.5 hours under fire. Constructing such a bridge required phenomenal coordination among hundreds of men, each performing specific tasks in proper sequence. Bridge sections had to be assembled on the bank, then floated into position, then secured to sections already in place. All of this occurred while German artillery fired at the construction site, while machine guns swept the riverbanks, while the current threatened to sweep away partially completed sections. That this bridge was completed at all was remarkable. That it was completed in 9.5 hours was extraordinary. Or consider the Seine crossings, where 5 bridges went up in 72 hours along a front where every existing bridge had been destroyed. Each of those 5 bridges required extensive preparation work, precise placement, careful construction, and continuous maintenance against both combat damage and environmental factors. The coordination required to execute 5 simultaneous bridge construction projects while fighting was occurring on both banks demonstrated organizational capabilities that few armies could match. The human stories behind these engineering achievements deserve preservation and remembrance. Private Lawrence Jefferson, standing in the water at the Seine while machine gun bullets kicked up spray around him, continuing to work because stopping meant men would die. Lieutenant Colonel Kenneth Fields refusing evacuation despite his wounds because the bridge had to be finished that night. Master Sergeant Earl Hall patiently training new replacements in the midst of combat operations because every trained hand made the work go faster and saved lives. These individual acts of courage and dedication, multiplied across thousands of engineers throughout the European theatre, created the aggregate effect that so impressed and disturbed German observers. The efficiency of American engineering operations improved steadily throughout the campaign as units gained experience and refined their procedures. Bridges that took 12 hours to construct in August 1944 took 8 hours by December and 6 hours by March 1945. This learning curve reflected not just individual skill development, but systematic analysis of what worked and what didn't, followed by rapid dissemination of lessons learned to all engineer units. After-action reports from successful bridge construction operations were studied and incorporated into training and planning. Techniques that proved effective in one location were quickly adopted by units hundreds of miles away. The interaction between American engineers and the French civilian population in liberated areas added another dimension to the story. French civilians, who had endured 4 years of German occupation, watched American engineers arrive and within days restore bridges the Germans had destroyed. This tangible evidence of American capability and American commitment to France's liberation created goodwill that lasted for generations. French engineers observed American techniques and equipment, beginning a transfer of knowledge that would influence French military engineering for decades. The contrast between American engineering operations and what German civilians had experienced with their own military was stark and instructive. German military operations had always prioritized combat units, often at the expense of support services. German civilians had grown accustomed to slow, inefficient interactions with military authorities. American forces brought a fundamentally different approach, where support services, including engineers, received resources and respect equal to combat units. This difference reflected broader cultural and organizational differences between the two nations. The role of African American engineers in these operations must be acknowledged and celebrated. Many engineer units contained significant numbers of African American soldiers who performed with distinction despite facing discrimination both within the military and in American society. Their contributions to bridge construction, road building, and all other engineering tasks were essential to Allied victory, and their service helped pave the way for eventual desegregation of the American military. The weather conditions under which many of these engineering operations occurred made the achievements even more remarkable. European weather during the winter of 1944 to 1945 was particularly severe, with heavy rains, snow, ice, and bitter cold. Engineers worked in these conditions for hours at a stretch, standing in freezing water, handling metal equipment that conducted cold through gloves and clothing, maintaining focus and precision when their bodies were approaching hypothermia. The physical demands of engineering work under these conditions were enormous, yet the work continued without significant slowdown. The logistical challenge of keeping engineer units supplied with the materials they needed was itself a major undertaking. Each bridge required specific quantities of standardized components that had to be manufactured in American factories, shipped across the Atlantic, moved through the supply system in Europe, and delivered to engineer units at the front. The fact that this supply chain functioned reliably enough to support construction of hundreds of bridges testified to American logistical capabilities that complemented engineering capabilities. Looking at the German response to American engineering reveals much about the limitations of German military thinking in this period of the war. Rather than attempting to develop equivalent capabilities, German forces focused on destroying American bridges after construction. This approach occasionally succeeded in damaging or destroying individual bridges, but American engineers simply rebuilt them, often within hours. The German approach treated each bridge as a unique target requiring focused effort, while Americans treated bridges as standardized products that could be mass-produced as needed. The influence of American combat engineers extended beyond their immediate tactical contributions. Their success demonstrated that properly trained and equipped specialist units could decisively influence campaign outcomes. This lesson influenced post-war military organization in the United States and Allied nations, leading to greater emphasis on specialist capabilities across all branches of the military. The story of American engineers in Europe resonates because it illustrates how ordinary men performing unglamorous but essential work can shape history's course. These were not generals planning grand strategy. These were sergeants and corporals and privates standing in cold water assembling bridge sections, driving trucks loaded with equipment to river crossings, operating bulldozers to prepare approaches, doing the detailed, demanding work that made strategic plans viable.